In this lecture, I am going to be reviewing Thermodynamics 8, and also I'd like to review our derivation that got us to a delta G of non-standard condition, the spontaneity or direction of a chemical reaction when you're not at standard conditions. Okay, so we left off talking about delta S of the reaction is equal to the delta S of non-standard conditions minus R ln of Q. This Q, of course, being a reaction quotient, which is basically the concentration of products to their coefficient exponents over the reactants in some concentration over their um, uh, uh, coefficients. Okay, now we saw that concentrations can change entropy. That's what this equation is about. Obviously, if you have a more dilute solution, if you get more dilute, entropy increases. And I'm not going to review that derivation, but that's what the Q is. Now, delta S of the reaction equals the non-standard condition minus the universal gas constant, okay, and which is nothing more than a fixing factor that talks how particles are independent of each other, molecular motion, times the natural log of the Q. The natural log, of course, is nothing more than taking the power of E, some exponent of E, okay, and taking that exponent, and that basically, if you take some kind of growth, some value of E, whatever that number is, okay, what natural log does, obviously, is take that growth and put it into a multiple unit of E of some form, an exponent of E. And E basically, guys, is natural growth that we use in all types of physical science uses. And it comes from the idea that it takes one thing and it breaks apart into other things. Those things break apart into other things. And that growth of one thing breaking apart, and we can use that in terms of money being compounded, or you can in terms of cells dividing, or molecules dispersion or disperting, um, leaving, I should say. I can't find the word. We can use that natural change, so that pops up everywhere. So what you should know that because it's a power of E, what we're doing is we're actually tempering that change. So as um, the Q goes up, okay, you don't times it directly, you have to make it into a multiple of the growth, okay, and that kind of tempers it and levels it out a little bit. So it's not basically based on exactly Q, but a multiple growth of Q, okay, and if I can explain it that way. And we'll see that in many different types of equations from then on in, here on in, I should say. Okay, so what are we talking about? Well, let's again do a basic derivation. Delta G non-standard, okay, is going to have to equal or have some kind of a value based on delta H standard minus T delta S standard. Now, how do we do that? Well, knowing this relationship based on dilution of a gas or a concentrated solution, we know that this, okay, can be put in for this delta S here. Okay, delta S of the reaction. Okay, we're going to put, and this whole being right here. So we get minus, okay, and I'll put it in blue, okay, T, I'll keep the T in black, T, okay, and delta S of, and by the way, I should have put this here. This is a standard condition. So delta S of the reaction, non-standard, equals the standard minus that. Okay, and of course that makes sense as you have a lot more, let's say, products, okay, and that means you're getting more, let's say, concentrated. Your entropy has to decrease, and if you notice, this number becomes a bigger number. If you have a lot more reactants, okay, as we talked about, then you know that the entropy is going to get negative, and you're going to add to it and increase it, okay? And then basically what we're talking about is Le Chatelier's principle. Add more products, the reverse reaction wants to go. Add more reactants, the forward reaction, even though this is now entropy. But in any case, getting back to this, put this in for delta S of 0. What do we get? We're going to get um, delta S minus R ln of Q. And we get delta H here. I guess I left it in black. All right, big deal. Now, this, of course, is delta G of 0. And this part, okay, R ln of Q, gets left over. But now understand, because we're timesing by T, negative T all the way through becomes a positive T, or RT, I should say. It's the designation they do it, RT ln of Q. And that's how we come up with non-standard delta G equals the thermodynamic tables that we use plus this adjustment for what the concentrations are doing. Okay, so what does it mean? Well, I guess it means that if my Q gets bigger, then my products are more favored, okay, or I have a lot more products than I'm supposed to. And gosh darn it, that means this makes a bigger positive, and this positive can make this delta G become positive, and it's what? Non-spontaneous. This is Le Chatelier's principle. A plus B, okay, in equilibrium C plus D. We're pretending we're not in equilibrium, but if you were to increase your products, my friends in chemistry, that would drive the reaction in reverse, because as we said last year, increasing the products of reaction equilibrium is going to favor the reverse reaction to lower these values. C and D are going to react a lot more to recover or make more A and B. Now in truth, this arrow means that we've just made the reverse reaction negative and the forward reaction is positive in delta G. We've made the reverse reaction occur, which would be made the forward positive. So anytime we talk about delta G, we're always talking about the forward reaction. So if you can see that by adding a lot more products, okay, this becomes a positive value for the forward reaction, okay? And the reverse is also true. If you have a lot more reactants, then my friends in chemistry, what you're going to do is those reactants are going to make the forward reaction go forward. And as you know, if Q is the products over the reactants, and the reactants get bigger, this makes this a negative value, right? The natural log of a number smaller than 1 is negative, and that's going to be added to the negative, okay? So if this is a positive value and I increase my reactants, I can force something that's non-spontaneous into being spontaneous by making this negative enough. All right. So that's the basics here. So let's get rid of most of this again. Now, before we do that, I have one more reaction that I want to break down for us that we're going to need for your other homework assignments. And that is, if we know delta G, non-standard, is equal to delta G of 0, okay, plus RT ln of Q, okay. And by the way, that R is going to be the gas laws in joules. That's going to be the universal gas constant in joules, because delta G is actually, if you remember, Q, it's joules. We divided by 1 over T to get rid of that T, because it really was entropy. So that's energy, joules there. So this has to be in joules as well, as a reminder. But given our non-standard way of attaining delta G, or spontaneity, or the change of the entropy of the universe at non-standard conditions, okay, we can make one more derivation. It's really quick. When the reaction is at equilibrium, delta G, okay, is equal to 0. So when the reaction gets to equilibrium, there is no work being done. There's no free energy. There's no directionality, because the forward reaction equals the reverse. So if I make delta G 0 at equilibrium, we get a new equation that we can use for evaluating evaluating K, or something called the equilibrium constant. Okay, so let's look at that here. So let's make this 0. That's plus RT ln of Q. And now, and I made the wrong 0. Okay, it's going to be the non-standard 0. The delta G, of course, at non-standard conditions is going to be what it is at those conditions. It's not going to change. So what's going to happen is, let's solve for delta G. And delta G, non-standard conditions, is going to equal to, well, you're going to subtract this whole term, negative RT ln. Now, we don't use the word Q or reaction quotient when we're at equilibrium. We use something called K. It's exactly the same thing as Q. It's the what? The concentrations of the products or the partial pressures of the products over the concentration or partial pressures of the reactants to their coefficient exponents. Solids and liquids don't apply. So it really tells us a snapshot of what these concentrations are. It's a reaction quotient at equilibrium. We call it K because it tells us something. When the reaction achieves equilibrium, what are the relationships of these products and reactants? And it's something chemists want to know for reactions because there's a tie in here. So let's rewrite this a little bit. Delta G, okay, 0 at standard conditions is equal to negative RT ln natural log of K. Now, if K is large, it's going to make this tremendously positive, and that should make sense to you. If I have a large K, which means I have a lot more products than reactants, because K is that ratio of products concentration over reactants. If I have that scenario, the reaction is tremendously and exogenic, which is the same thing as saying very spontaneous. So when you look at a way to look at this, let's look at the bottom of a kind of a hill here in terms of the K. And if the K is really large, I'm going to draw it like this. This is K, and this is where my delta G non-standard is equal to 0. K is equal to some number, equal to the quotient. But if K is a large K, that means there's a lot more products than reactants once we reach equilibrium. This right here is the reactant side, a lot of reactants. Over here is the products. Okay, so this is the point of equilibrium. Now, what this means is if I have a large range, you can see to the left-hand side, okay, of possibilities for my delta G. Now, I know that when we're at K, delta G is 0. But what I'm saying to you is that knowing what K is, it affects, okay, our reaction, our non-standard delta G in a certain way. Let me explain. If we have a lot more reactants, the reason why a large K gives me a very negative delta G standard is because if I have a K that shows that there's a lot more products favored, this K is swung over. If I had a drawing like this, it's like K is equal to 1, equal number of products. My K is swung over to the right. It's a large K. That means if there's a lot of products, A plus B going to C plus D, and there's at equilibrium, these products are favored. That means at equilibrium, there's very little A and B, which means the reaction loves to go to the right. And if it does so, delta G is very negative. So in any position here for Q, the reaction tremendously goes forward because, as something you should know, reactions always go toward their K. Always. So if you don't have enough reactants, and we would say in this case the Q, which is the products over the reactants, same thing, okay, the concentrations to the stoichiometric coefficients, okay, if the Q is smaller than the K, what does that mean? There's not enough reactants. Okay, this reaction goes tremendously in the forward direction. Now, as you start adding more and more reactants, we start getting closer. As you start adding more and more products, Bad Grotsky, this delta G, or the Q at this G, non-standard, gets closer to K. And of course, okay, if that if as closer you get to K, the less spontaneous you are. So the tie-in here is how far away are you from K shows you how spontaneous. So if you have a little bit, tiny bit of reactants, okay, they're going, and you have no, listen, look at that, just about almost no products. This is going to really go forward. It's only when the products start building up to some value, but it's going to be tremendously high if K is high, that you start having the reverse. So this position goes here, 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 and here, and all of a sudden, once I add too many products, now I'm in this position. And I always say that what? Delta, the Q or the reaction always goes toward the K. So if you have a high K, you need a lot of products to go past that point in the reverse. And if this happens, if you had too many products, Le Chatelier's principle is going to state the reaction is going to shift to lower that P. Well, it only does so, okay, if you add enough of them past that K. And delta G in the reverse would be negative, but delta G in the forward now is positive. So delta G is negative in these positions, and there's a lot of them if K is large. Okay, so that's the basics of all of this. So a large K means delta G very negative. Of course it is. That means a lot of positions are really farther away from K. Now, of course, the opposite is if you've got a small K, all right, if you've got a small K less than 1, this becomes a negative. Now delta G is positive. So if you've got a K, and I'll draw this over here, you've got a small K, all right, a small K, that means you're kind of over here. K is equal to, and again, it's a bad drawing because I should draw it like this, okay? The K is over here, and we have delta G non-spontaneous equals 0 at this point, but at non-standard conditions, I can be at any place. So having a small equilibrium means that it's very possible, very easy to have a lot more, okay, products than reactants. So the reaction, in this case, if the Q is larger than the K, the reaction is going to go in the reverse. And delta G of the forward is positive. And that should make sense. So low K makes this a positive, okay, makes this a negative number, a number smaller than 1, okay, gives you a negative number here, makes this whole expression positive, all right, and therefore your G is going to be positive, okay, and non-spontaneous. So the link is very important. What is the Q compared to the K, and where are you in the reaction? Okay, now if they ask you to solve for K using the reaction, we do this, but in the back of our minds, we need to start thinking about where we are in a non-standard reaction compared to K. If K is large, it's hard to be behind it. You're mostly going to be in front of it, meaning your Q is too small compared to K. Not enough products, so you're going to make more products, and as you make more products, your non-standard G gets closer and closer to G. We always go toward K. If you add too many, it's going to go back. This is essentially Le Chatelier's principle in terms of concentration. Now, the only problem with this that some people have is the math. Because if we're going to solve for the ln of Q of something, we have to make particular counts of, we have to remember our math a little bit. So, when you deal with something like ln of Q, okay, and you're solving for it, let's pretend that we're solving for this equation. Let's do this equation here. And let's say we're going to solve for something in Q, like the problem above. Well, you know that at equilibrium, okay, in this case, the problem above states that find the minimum partial pressure of the N2O4 at which when the temperature is 127 and the partial pressure is 0.5. So trying to find part of a Q. So this is going to be ln, okay, of now NO2, if I look at my reaction, is my product. So I put that there, 0.5, and of course it's squared because of that exponent, and that's all over this concentration, which is my x to 1 power. Now what does that equal? Well, that's going to equal okay, they want the minimum, okay, it's going to be equal the rest of the expression that we can plug in, because you're going to find delta G through the tables, okay, non-spontaneous. So you're going to have this, okay, and we're going to solve, let's say, to find the minimum that occurs. Now in this reaction, we're going to set delta G to 0 to find exactly when, to find that actual concentration where we find that break-even point, that threshold like we talk about. So we set this as 0, and we're going to solve for the rest of the reaction. Of course, we're using this reaction here. So we set this to 0, and you notice we're going to solve for RT ln of Q, okay, and basically you're going to have some values here and some numbers. And how do we deal with this? Well, to get out of this, you do E of the x of both sides. So whatever this number is, you do E of that number, and of course E to the x of this just becomes 0.5 squared over that x, and then you can find the E to that number and solve for x. So that's the only little thing, whether you're using this equation in this worksheet, or you're using this equation for the other worksheet. So please try those. Hope this was kind of clear. I hope it was crystal clear, but it is a tough concept. All right, take care.